Okay, so this is going to be another video, chapter 3, towards the end of chapter 3, AP Statistics with linear regression. What this will kind of talk about is that R and R squared value and where it comes from. And let me just say, you probably will not need to ever calculate an R value by hand or an R squared manually. As you know, when you do the linear regression equation in your calculator, as long as your diagnostics are on, it's going to pop up in R and R squared. And for the most part, you'll just need to know how to interpret those values. But this is just a little bit where it comes from. Um, and maybe like in a bonus problem or something in my class, I might have you do something like this. But to get these values, let's take a look. Here's some data here. Let's just say you and some friends are taking an ACT review course, and you kept data on 3 people. How many courses did they attend, and then the score increase on the ACT. So there's the data. Person 1 attended 3 classes, and their score went up 5 points, and so on. So this the R and R squared, again, kind of measure the correlation, and then they also measure the R squared measures the percent variation in the Y value that can be explained by the model. So let's look at how to calculate these and where they come from when your calculator does this. Let's go ahead and jump into R squared first. So this is our data again. What we want to do when we go and find R squared, what you want to do is first, I just made a plot. I guess you don't really have to make a plot, but it's going to help us visualize a few things. So I just made a little plot. I'll talk about some of those numbers in a second here, but the important question here is if we needed to estimate the ACT score increase, if we want to, estimate a Y value, and we did not know the X value, okay, we just want to make some blind estimate, we can just use the average of our Y values. Okay, like if someone else walked in the room and we just said, what's your predicted ACT score? And I have no clue what the linear regression equation is, or I don't even know how many classes they took. I would just go by the values I have and find that their average is 5. Okay, the average of those 3 Y values. So I plotted that there. Y equals 5, you see the red line there. And then what I did was I want to see how far away or how much error was there from our values. Okay, so for instance, our first point, the 0.35, so that point was right, where we at, 3.5 was right here. Okay, so that point was exactly at the average. Maybe that we just kind of got lucky. It was just a coincidence. So that had an error of 0. Okay, the 0.12 we can see is up here. And in yellow, you can see that the residual of that, the error of that was 3. It was negative 3 because we were 3 points below the predictor. Okay, in this case, our predictor, again, is just the mean. And then the third point, 6.8 up here. Again, we were predicting the Y values to be 5 because that's what the mean is. So our Y value was technically 8. So it had a residual of positive 3. Okay, so what we want to do then is again, we deal with squared errors all the time. I don't want to worry about negative numbers and so stuff like that. So what I do is find the errors from the mean, and I square those. Okay, and I'm going to add those up. So the negative 3 squared plus the 0 squared plus the other 3 squared. So those are those 3 yellow numbers. Everything's kind of color coded on here. So 9 plus 0 plus 9. So we get a total area of 18, or total error, I should say, not area, error. And we call that the SST, T just for total error. Okay, again, based on using our mean as a predictor, the total error, sum of those squareds was 18. Okay, and then what we do is say, all right, I can get an equation from the calculator, a linear regression equation, and I want to see, does that do a better job? Like, are the sum of the residuals of the actual best fit line, is that it should be less than 18, but I want to see how much better is it, basically. So that's going to be our next step. Okay, so again, to kind of summarize up here, so 18 is going to be the sum of the total variation from the mean. So how much is still unaccounted for by the actual line, like if we actually did the linear regression? So what I did, I went into the calculator, I had my data in L1 and L2, and I came up with this equation, basically the predicted increase. Okay, so increase with the hat on it there is 1.18 times the classes plus 1.052. Okay, and what I did was I made a plot of that. Okay, and I'll talk about this table in just a second here. So the blue line there, that's the actual regression line. And we can see that each point still is not directly on the line. That's fine. There are some errors there, some residuals there. Okay, so I I kind of tried to line those up. The top one here that's circled, the 0.39, that's going to be the vertical distance from the actual line to the first point. Okay, and so on. You can see the second one was slightly below, so it had a negative residual. This point had a negative residual. So I was just setting the table up the way we did a little earlier in the chapter, where L2 was the actual Y value, and I did L3 was the predicted Ys, and so on, like the previous example stated. And what I see now is there are residuals again for each point, just like there was on the previous slide. And I can find the sum of those squared residuals also. Okay, so I'm going to take the 0.3974, square it, plus the negative 0.2368, square it, and the third one as well. And that's going to give me the sum of the squared errors, or basically the sum of the squared residuals. Okay, now keep in mind the line, okay, the linear regression line was found by minimizing this number. That line is the line that gives us the smallest SSE here. That's the whole point of what a linear regression line is. Okay, so there's still some error. There's still 0.2389 error, even with our best fit equation. Okay, so that number there, that's the amount of variation that's still out there. It's unaccounted for, even by using the real line, the least square linear regression line. There's still some residual error. Okay, it's a lot less than what we had before, though. Okay, so what we want to do is figure out what percentage of the error is unaccounted for. Okay, so what I'm going to do is go back to my other page. Again, our total variation from page 1, that was when we got 18. We just saw the variation unaccounted for by the line is still the 0.2389. So you get this fraction here. Okay, the SSE, okay, the sum of the residuals divided by the sum of the total. Okay, so that's about 0.013, so around 1.3%. That's the proportion of the total variation. Okay, 18 was the total. We had 0.2389 still out there. So about 1.3% of the variation is not accounted for by the line. Okay, and what R squared is asking you how much is accounted for by the line. So what we just need to do is take our number that we got and subtract it from 1. Okay, and we will get this number. This 0.9867, that will be your R squared for that situation. If you use a calculator and check it out, that's right. And again, what it's telling us is its interpretation is you would say 98.67% of the total variation of the Y variable in this case, which was scores, is accounted for, or you could say is explained by. So it's accounted for by the linear model, which was the regression equation that the calculator got us. Okay. And that's your R squared value. So it's saying basically those taking more courses, that was the X value, right? We were talking about number of courses and then score increase. So number of courses, score increase. So we're saying almost all the variation, right? 98% of the variation in scores increases can be explained by the number of courses. Okay, so there's only a little bit, there's only like there's actually this percent, right, the 1.3%, which is explained by other variables other than the number of courses. Okay, so that's R squared. Now R, to do that's a little complicated too. Let me walk through some of this. I know it looks like a lot up here. Basically, if we just start with, here's our original data. Okay, that's L1 and L2. Now what ends up happening, let's look at this stuff in a second. Let me give you a visualization. Here's my 3 points. Okay, there's one right there, one's right there, and one's right there. Okay, and now what these dotted lines are, these are actually just the means. Like if I went back up to my list and just found the average, actually I have these listed here, the average X value and the average Y value. Okay, just one variable stats for each of those. And I also have the standard deviations below we'll use in a second. But that's all that's plotted here. You can see the Y bar, the average Y values were 5, so I just drew a line there. And the average X, I think, was 3.33. And the reason I put those in as dotted lines is because there's a special property that says that point where those two things meet, Okay, so that point is x bar, comma, y bar, whatever those averages actually are. That point will always be on the regression line. Okay, it's just a property. It's just, they just always do. But here's where it helps us with thinking about what this R value represents. Okay, basically what happens is you take a look at the 3 points, or all the data points, I guess, technically. So there's our 3 points in blue. And what we want to do is ask ourselves, you know, are those showing a positive correlation, a negative correlation, and also strength will come into the mix here because R tells us both things. So what we actually do is we convert things to z-scores. Okay, so for instance, this value here, the actual coordinates of that point, okay, which one was that? That was the 6, 8. Okay, the actual coordinates are 6, 8. But if we change those both into z-scores and say, you know, how many standard deviations is the x value above the mean x value? Okay, so if I wanted to change it into the z for the x and the z-score for the y, it's the same formula we did earlier in the year. Z-score is just going to say, you know, take this value minus the mean and divide by the standard deviation. We're going to get a z-score for that. Okay, so again, this originally is just an original xy. We're going to change it into its z-scores. And that's what I did up in the table in the calculator, just to kind of help me. So you can kind of see what I did in the formula. I went and said, you know, this was like in list 3. I said, I want to take every value in list 1, okay, which is the x value. And you can see I'm subtracting the mean, and then I'm dividing by the standard deviation. Okay, so it's telling me, for instance, that this x value of 3, it's negative 1.311 standard deviations. That's how many standard deviations it is below the mean. Okay, and then I went and did the same thing with the y values. I took the y values are all in list 2 originally. I subtracted their mean, which was 5, and then I divided by its standard deviation, which was 3. And I got a z-score for each of the y values. Okay, and then what you end up doing, I'll come back to the table in a second. So this 0.68, let me write those numbers down. It was the z-scores of those were 1.0608 and 1, right? So the z-scores were 1.068, and the z-score for the y was 1. I was 1 standard deviation above the y values, and I was a little more than 1 above the x values. So what ends up happening is you end up thinking about these as making like a square, basically, from here and into here. Okay, and pretend like that blue line, the actual linear regression line, is not there, because that just happens to be there. But what ends up happening if the length of this thing was the z-score of the x value? So it's just basically a rectangle. The length is the x value, the height is the y value, and it has some area to it. Okay, this whole square has some area. Okay, this square down here from this point, it has some area. It's here to here to here. Okay, it has some area. Now the third point happens to be right on the line here, so it technically doesn't have a height. It's like its zy would be 0. Okay, if we can check that. That was the first point up here. The z-score of the y's was 0 because its y value was exactly what the mean was. So that one doesn't really have any area. But where this r value comes from is it's adding up those areas, and it's basically finding the average size of those. So for example, anything, if you think of, let's think of our x and our y axis as as where the actual means are. Okay, and any points up in this top right quadrant, it's kind of like the first quadrant. Anytime there's squares up here, those are going to be positive contributors to our R value, because positive correlation means it's up and to the right. Also, any areas down here are going to contribute positively to our R values. Okay. If there were some points, and in most data sets when you have a lot of points, there'll be a few down here. Okay, and anything down there would contribute negatively to our correlation, as well as anything in here. Okay, so what we need to do is add up all of those square areas. Okay, so that's kind of what I did in I think this would be L5 over here on the far right. I said, you know, if I were to take the zx times the zy, I would get this product right here. Okay, so I'm doing zx times zy. It's list 3 times list 4 if you're using your calculator. And I'm getting these 3 areas. Okay, notice they're all positive numbers. Okay, so what happens is we add those up and you actually divide by n minus 1. And that answer is going to give you the R value. This actual answer is the R value. Okay, so in our case, if we added up all our areas, it was 1.986. Okay, I'm down here. That's the sum of the things in list 5, which was the zx times zy. And I divide that by 3 minus 1. It's kind of like when we did standard deviation. You divide by 1 less than however many points you have, and there's a reason for that that'll come up later in the year. But basically, that gives you your correlation, and that gets us a 0.993. So that means it's a very strong positive correlation. And you can see, kind of from the graph again, the blue shaded quadrants give us positive correlations, and all of our points were either in there or they were 0. We had nothing negative to subtract from it. Now, if we threw a point that happened to land down here or something, notice that's going to give you a big negative area that would need to be added into the other ones, and it might even be enough to sway and make the whole thing go negative, or it's definitely going to make it get closer to 0. Okay, so just kind of tying this all together, one last thing, if let's say you want to get the equation by hand, and let's just say you have some x and y data, and we have some points here. If you want to get the equation by hand, you're going to need to know the x bar and the standard deviation of x. You'll need to know the y bar and the standard deviation of y. So you can use your calculator to get those. And then what you can do is you can figure out r like we just did. Okay, it's going to be the sum of the z-score square areas divided by n minus 1. And then what you can do with that is to go to your next step, you can say, all right, once I know what r is, remember the linear regression equation is this. Y hat equals the b0 plus b1x. Okay, and what we can say is the formula for slope, which is on your formula sheet, uses that r value that you found up here times sy over sx. Okay, and then you're going to say, all right, because you already found r, sy and sx, you're going to know from over here. You can find the slope, and then you can go ahead and say, all right, now that I know the slope, I know that y bar plus the intercept is a thing where you're not going to know. This is basically just using the fact that the means are on the line, so you can plug them in, and you're going to know those means from the step 1. So with the bonus problem I'm sending out, you can kind of follow that procedure, or you can do something else. But hopefully that helped a little bit. I know it can be a little confusing, and again, you're not going to have to do a lot of this stuff by hand. But hopefully that helped clear up a little bit of what's going on behind the scenes with these formulas and these values.